we discuss in this video about minimization of automata. What this really has to do is with the idea that a language can be given by several different automata. So you can have the same language presented as the language of automaton A, but it can also be presented as the language of automata 2 and so on. So you can have quite many automata. And in fact, we have seen examples of this type, some of them non-deterministic, some of them deterministic, but even if you stay within just one single type, let's say you only think about deterministic automata, there can be many different automata that give the same language. And so we think about equivalent automata in the sense that they give the same language. And obviously, among these equivalent automata, to describe the language, you would like to have the simplest one. And one way to define what the smallest or simplest, so smallest automaton recognizing L. So what I mean by smallest is the one with the smallest set of states. So that makes sense, right? You have you need to present the language, and you will present it in terms of the minimal number of states that you really need to recognize that language. And there is a result that, in fact, I'm not going to prove in this course. I come back to this point, why don't I prove it? But I will do a large part of what's needed to understand this result. And the result is, for any recognizable language L, there is a unique, and stress is on the word unique, minimal automaton recognizing L. What this result says is, so you have many automata recognizing L, and you try to choose smaller and smaller automata until you find a minimal one. And the result is saying that the minimal one is in fact unique. Whatever method you use to find a minimal automaton, the result is always going to be the same. There is only one single minimal automaton recognizing L. And this uniqueness of the minimal automaton, I'm going to prove this particular part of the result, the fact that it's unique, because for this I would need to define a little bit more algebra than what I really want to define in this course. So I'm going to skip the uniqueness part, but what I will focus on, in fact, in this lecture, and in fact in another lecture that it follows this one, is this part, building the minimal automaton. How do you, in practice, build this automaton starting from language L or starting from an automaton, whatever automaton, recognizing L. So that's what I want to do in this series of lectures about minimization of automata. But keep this in mind that, in fact, once you got the minimal automaton, there are many methods to build this, but the result is always unique. There is a single one recognizing that language. And if you think about it, it's not obvious that the minimal automaton should be unique, but this is true. And in this particular lecture now, I just want to introduce the intuition of what it means to go to a smaller automaton and eventually go into the minimal automaton recognizing language L. And what I'm going to do is, let's take an automaton, right? So I'm going to take an automaton made of states Q and alphabet sigma, and I take a deterministic automaton given by transition function delta, Q0 and F. And so this is a deterministic finite automaton. And I'm going to define, so for Q, for some state in Q, I'm going to define an associated automaton, AQ, which is almost the same as this one. It certainly has the same states, it certainly has the same input function, it even has the same transition function, and it even has the same final state. It's just that it starts from Q. So what this automaton is the automaton recognizing all the words with successful computations starting from state Q. So Q is now your initial state, as opposed to the original one that had Q0 as the original state. And I want to give this definition, and this is going to be really the key definition driving our quest for a smaller and smaller automaton recognizing a language. The definition is the following. I'm going to have two states in this automaton, and I'm going to have k, a number greater than or equal to 0, and we say that P and Q are k distinguishable. So I can make a difference between states P and states Q in automaton A if there is a word U from the input alphabet of length at most k, such that when I do a computation starting from P in U, maybe I'm going to say something else, and then I reformulate this in the way that I wanted to write it, such that AP accepts U while AQ rejects U, or the other way around. So what this means really is that you will say that P and Q are k distinguishable if in the automaton A you will have something like this. You will have a computation starting from P and going with U, and the length of U is at most k. And you also have a computation obviously from Q going with the same input word and going to some state S. And so you will say that P and Q are k distinguishable if there is a word U of length at most k that makes a distinction between these two computations. So if one of these computations is accepting while the other is rejecting. And so you have this idea. And so intuitively, what I mean by this is that from the point of view of the automaton A, you want to minimize these automatons, right? And so you will do that by eliminating some of the states. And the basic question you have in front of you is, which states can you afford to eliminate? So in other words, which state doesn't really bring anything new in addition to something you've had in some of the other states? And obviously, if you have two such states, P and Q, one of them leads to a successful computation, the other one leads to an unsuccessful computation with some input. Clearly, P and Q bring different values because they can distinguish between word U. P does something on word U, Q does something completely different on word U. So you need both because they give you different aspects of computations on word U. So I hope that this makes sense intuitively. If it doesn't, pause this video now and maybe look at it again and look on the lecture notes as well. This is the crucial insight that we are going to use in this relatively complex construction we are going to make over the next 1 or 2 lectures. Once I have this concept, I also say that two states, so two states P and Q from Q are equivalent if P, Q are K indistinguishable, so meaning they are not distinguishable, they are not K distinguishable for any K. So they are K indistinguishable for all K greater than or equal to 0. And so, again, intuitively what this means is that once you got to state P with some computation, it doesn't really make any difference if you're in state P or in state Q. Any computation you run from state P with some input word gives you exactly the same result as if you were running that computation from state Q on the same input word. So intuitively, it looks pretty obvious that these two states really don't bring any additional value to what your automaton does. So instead of 2 letters, instead of 2 states, you can certainly keep just one and eliminate the other one. So again, the insight is once you got to state P with some input word, it doesn't make any difference whatsoever if you are in state P or in state Q for the rest of your computation, because from P running a computation with whatever input word is the same as running a computation from state Q with that input word. The result is going to be the same, accepting or rejecting computations. This is the essence of the notion of equivalent states. And then we have this lemma saying that one of 2 equivalent states can be removed without changing the language. So I want to prove this, and so what I mean by this, maybe this also includes a more formal specification of the result. So again, I have an automaton made of these states, input alphabet, transition function, initial state, and final states, and we have P and Q 2 states. And they are, as a matter of fact, they are equivalent. So I'm just going to write this. They are equivalent. And I'm going to define a language or an automaton that has the same states minus one of them. Let me just trace back one step to make the point of which state I'm going to remove. So I will say this. I remove, so from P and Q, I remove the one, or I remove one that is not the initial state. I don't want to remove the initial state, obviously. And in between P and Q, maybe both are different than the initial states, but certainly one of them is different than the initial state. So I'm going to remove that one. And so I say assume P is different than Q0 and remove P. If P is in fact equal to Q0, just eliminate the other one. But I'm going to assume that P is different than Q0, and I'm going to remove this one. And so here is how it goes. I'm going to build a new automaton, and I'm going to make the point that it accepts exactly the same language as A. and this one is going to have exactly the same states minus p. I don't need p, and I'm going to show you in a moment why don't I need that one. The transition function is almost the same, but with a small difference. I do have the same initial state. Remember, I made some extra effort to make sure that I don't eliminate by mistake the initial state, and certainly the same final states, unless p was there, in which case it got eliminated. So this transition function delta prime of, say, some state r and letter a is going to be exactly the same as before if this one was not p. So if it's not p, I mean, I just keep the same as before. But if it is p, then I'm just going to define it to be q. Because remember, p and q, I'm just writing it here, p and q, they were equivalent. So that's what I do. Right? So this makes sense. The transition function is exactly the same as before, but whenever the original automaton was saying you go to state p, I don't have state p, but I have the equivalent one, state q. So I would say now you go to state q. And if we think about the computations in these two automata, so if I take a word w in sigma star, and w is made of letters a1, a2, an, n greater than or equal to 0, and these are letters. And I'm thinking about the computation on A. And the way this goes is it starts from Q0, and it goes with A1 to Q1, and with A2 it goes to Q2, and so on. And so this is a computation in A, and if none of these states is P, then this is a computation of B as well. So the same computations that A does, also B will do, unless the computation visits state P. Now, if some of them are P, so in the other case, let Qi be the first occurrence of P. So first occurrence meaning that I is the smallest index such that Qi equals P. So what the computation of A does is I have Q0 and A1 goes to Q1 and so on until I get to Qi, which happens to be P. And then I continue AI plus 1 goes to Qi plus 1, and all the other ones. So in this computation, from state P to the end, I go with the word AI plus 1 all the way to AN. And remember now that the states P and Q, they are equivalent. So that means that the computation from P will have the same outcome as the computation from Q on the same input word, meaning that it's accepting in the same conditions and it's rejecting in the same conditions. So in my automaton B, I can simply just do this computation. I go through the same states. None of this is P because this is the first time I had P in this sequence of states. And whenever my automaton A was attempting to visit P for the first time, I'm actually going to visit Q. And then from Q, I'm going to just run the computation on automaton A with this input word. And that's going to take me to whatever state, and they will be, accepting or rejecting computations in the same conditions. So that shows that indeed I can get rid of one of the states without missing anything. I'm going to accept the same words, and I'm going to accept I'm going to reject the same words in the two automata. So this construction succeeds. So this is our insight into building smaller automata for the same language. We will have a strategy of finding which states are equivalent, and once we did that, for each equivalence class, we are going to have just one representative. The other ones are not needed. So we are going to look now in the next lecture for ways to identify indistinguishable states. And for each class of such indistinguishable states, we will keep just one representative, and that's going to bring us to the minimal automaton.